All right, we're going to take a look at the third topic in the thermodynamics section, which is sensible heat versus latent heat. In this section, we're going to look at a couple of questions before we get started. Some of you may be familiar with sensible heat and latent heat already. For some of you, you may not have covered it in your classes yet. The questions I want you to think about before we get started are, first of all, does a change in heat always result in a change of temperature? I think we've already alluded to that fact, alluded to what the answer for this question should be. So does a change in heat always result in a change of temperature? Secondly, I want you to think about, does the temperature of water keep increasing after it begins to boil? I'm thinking about the water, not the steam. And thirdly, we want to think about what happens to energy when ice is formed. So let's just think about what happens in these scenarios, and then we'll get into where we can do a little bit of calculation. Does heat always result in a change of temperature? Well, I think for us to answer this question, we really have to look at the two scenarios below. The answer to that question is no. Heat doesn't always result in a change of temperature. Okay, sometimes heat is going to result in a change of phase. It takes energy to spread molecules far enough apart that they vaporize. For example, taking water, for example. That's what our next question looks at. Does the temperature of water keep increasing after it begins to boil? Well, if you've got water on the stove and if you put a thermometer in it and you've got your stove cranked and you keep adding energy to that water gets to 100 degrees. Occasionally, you could argue with me that sometimes we're able to superheat water a little bit, but it gets to a certain temperature and it starts to boil, and as long as there's nothing in that water, nothing else in it, it gets to 100 degrees and you can put all the energy in it you want. You're not going to get that water to go to 150 degrees Celsius, because at 100 degrees Celsius, that water begins to turn into steam vapor. And energy is required to turn that water into steam. It requires energy to turn the water into steam at 100 degrees Celsius, and then we could continue to heat the steam if we had the right equipment in order to do that. So the temperature of the water doesn't keep increasing after it begins to boil. The water temperature comes to a boil, comes to 100 degrees, and then for all intents and purposes, it maintains 100 degrees. It just requires energy to vaporize. Now let's look on the other end of the spectrum. Let's say we've got ice. Does it take energy to form ice? Well, yes, it requires energy. I wish it didn't require energy, because then my freezer wouldn't work nearly as hard. We know it takes energy to make things cold because, well, our freezers continue to draw energy because they're just not thermally efficient enough. They're pretty good, but not quite enough. So just because heat is changing doesn't mean we're going to have a change in temperature. So in this section, we're going to look at two types of heat. The two types of heat we're going to look at, we're going to look sensible heat and we're going to look at latent heat. Okay, sensible heat and latent heat. Sensible heat, I always say it's heat that makes sense. Temperature changes. Okay, with sensible heat, we get temperature changes. With latent heat, we get a phase change. But we can have both of those work together. Now, I did say, what happens to the temperature of water after it begins to boil? Well, what about your boiler? Our boiler, I happen to know, was set for 125 degrees. So if water never gets above 100, why set it for 125? And that's because we can increase the heat of the steam, which increases the heat of the system. So there is a little bit of, there are ways that we can maintain some control in order to cause the temperature to increase higher than normal. So when I say water doesn't go above 100, I'm thinking at atmospheric temperature. If there's atmospheric pressure, if there's any of you that want to get technical and argue some of the science on that. First of all, let's look at sensible heat. I find it's the easier heat to work with. It's an easy formula to calculate, and it makes sense to us. So sensible heat is heat that can be measured with temperature change. It's the heat we're used to thinking about. The temperature goes up 10 degrees outside. Well, that's an example of sensible heat. I put a pot on the stove. My water initially is coming out of my tap at maybe 10 degrees Celsius. In about 70 seconds, I've got it up to 100 degrees Celsius. That is sensible heat that's required for that. So I always think of it as, if you want to help remember, temperature, when a temperature change occurs, it makes sense that there's heat. So that's the sensible heat example. Okay, so sensible heat goes with a temperature change. Now, the amount of heat that is required for the temperature change depends on how much of the substance there is. So if you think back to earlier in the slide when we had the two beakers, now we could quickly go back to that image. And we said, well, there's less stuff in this beaker and there's more stuff in this beaker. So it's one that has more heat because it's got more water or more of whatever it is that's being heated up in it. The equation for sensible heat is going to take that into consideration as well. So it depends on mass, and we'll see in the equation for sensible heat, mass is included. So heat always depends on how much stuff I have. Sensible heat also depends on the ability of the material to absorb energy. Some materials absorb energy much better than others. And that's what this little C value is. This is our specific, apparently can't write. Spelling never was my strong point. All right, let's give her a shot again. So C is our specific heat, or the heat capacity. Okay, so it's a specific heat capacity of the material. So it's just a measure of how much energy that material holds, or how much energy it's able to maintain. Now let's think about it. We'll think about for a sec whether we want a high specific heat if we want to conduct energy, or a low specific heat if we conduct energy. So we'll look at that when we get a little bit further. If it has a great heat capacity, it means there's going to be more sensible heat, so we're going to get more of a temperature change. And it's also going to, it has a higher sensible heat, so it's going to hold more energy for that temperature change. Greater heat capacity also means that we're going to need more energy to get a small temperature change. Let's look at a few materials. So specific heat capacity, this is your C, and we're going to look at a table in a minute. I'm not going to put the table up just yet. I've got it on the next slide. So specific heat capacity is the ability of the material to store heat. It's defined as the amount of heat energy needed to change the temperature of any material 1 degree Celsius. Okay, so we'll find out most of it's related to, we're going to find maybe it's grams per degree, how much energy, how many joules per gram per degree Celsius. So you're always going to find the units will always be the energy unit that you need, you'll have a mass unit, and you're going to have a temperature unit. So we'll want to watch all three of those because our units will convert a little bit. So if we look at this little chart that we have here, this is a chart that shows us the heat capacity in kilojoules per kilogram. So how much energy per kilogram Each of these materials, so water, stone, wood, plastic, and paraffin, each of these materials absorb with a 15 Kelvin 15 Kelvin temperature change. That'd be the same as a 15 degrees Celsius temperature change because it's the temperature change. So notice water requires a fair bit of energy in order to change its temperature. Stone requires very little energy to change its temperature. It stores very little, a much smaller amount. Wood is a little bit better. Plastic's quite poor, but paraffin, it has the ability to store a huge amount of energy. So depending on these materials, we'll get different properties. Now, wood is a pretty good insulator for us. It's not the best, but not terrible. As opposed to stone, stone is not all that great at insulating. Actually, we have a cement slab, so you could think of that as being stone, and it has very little insulating properties. So basically, whatever the temperature is outside, that's the temperature of the slab in my house. And that's because it has a very low heat capacity. It stores very little energy, which means there's a much smaller energy difference between the temperature of the ground under that slab and the temperature in the room. So that's a room that we've actually added some wood planking and some styrofoam on it in order to make it warmer using what we know about specific heat capacities in order to make our heating bill a little bit better. So this section really relates to why we can use it to help us understand why we insulate with some of the materials that we do. So this chart is in the tables that I posted up after the last lesson. I'm going to post them in this section as well, just so that if you happen to not be sure where they are, you can go back to them. So this is the specific heat capacity for a number of materials, and you'll see your units change. So the very first table, we have calories. So there's 2 units. This number, 0.24, so that's the specific heat for air, is calories per gram degree Celsius, or it could be kilocalories per kilogram. So you can use both of those units with that one, with this one number. You can use either set of units. It's going to be either or. If we're looking at this column, we have joules per kilogram degree Celsius. And then over here, we have our imperial with the BTUs per pound Fahrenheit. So you've got your 3 different units that we will work with. Most of the time, we'll use this one. Okay, most often we'll end up using the center one, but do double check your units. If a question asks you for calories, you want to be in this side of the column. If it asks you for joules, you want to end up being in the middle. If it asks for kilojoules, you have to remember that this is going to give us joules as an answer because it's joules in the unit. So you'll have to work on doing a little bit of conversion. We're going to find we do a few conversions in this section just because the numbers are quite large. So let's just compare a couple of, just compare a couple of units. All right, sorry, I had to pause, so if I repeat something, you'll have to bear with me. So we were looking at which units we use most often. We use calories and degrees Celsius, we probably use the least often. Joules and kilojoules we use the most often. I know in the HVAC trade, BTUs are the ones that use the most there, but this joules and kilojoules are most often used for physics. Now, I think you'll find as the world changes and we move towards the metric system even further, I think you're going to see a shift from measuring energy in BTUs to measuring energy in joules and kilojoules. So that's something that I'm quite positive we're going to see happen. We're already seeing that happen with electric vehicles, and with electricity, vehicles are starting to be rated in watts as opposed to just in horsepower, and it's simply because of the evolution of a global economy and the types of energy that we're using. Now let's take a look at these values. I wanted to stop and think for a few minutes about how they relate in terms of being insulators. So the higher the specific heat of a material is, the better it will be at insulating for the most part. Now there are some exceptions to that, but in general, the higher the specific heat, the better it is at insulating because it holds a huge amount of energy. The lower the number, the better it is at conducting. So one thing I want you to think, but as we look at a few numbers, I want you to think about electricity. I know all of you have done electricity unit, and you know what materials conduct electricity really well. Gold conducts electricity the best. Unfortunately, it's really expensive. Electricity is energy, so we're going to see, is gold one of our best conductors of thermal energy as well. Copper is an excellent conductor in electricity, which is a conduction of energy. Is that true when it's temperature? I think even if we didn't know anything about specific heat, if we thought about how often copper is used in heating systems, we would probably assume that yes, copper is going to have a low specific heat. It's not going to hold very much energy. It's going to allow it to transfer easily. Imagine if our copper pipes stored a lot of energy. That would make them very, it could be quite inefficient for us because it would take a long time for them to heat up. And then, yes, they would hold that energy and maybe distribute it more slowly, but just purely the amount of time it takes them to heat up would be a little bit of a problem for us. And then let's think about a boiler in a home heating system. What's in that boiler? It's not air. We fill it with water. And why do we fill it with water? How much energy is water able to store? Is it just a matter of convenience that water is available anywhere, that it's non-toxic, or is there some other property? So let's just take a quick look at our table and we'll just do some comparisons before we do a few calculations. So first of all, I said the lower the number, the better it is at conducting. And we said, well, in electricity, gold's one of the best conductors. And if we look, here's gold in our chart. See if I can get a straight line. And 130. I'm going to actually see. Let's see if I can switch to a highlighter mode. There we go. So gold is able to store, only stores 130 joules per kilogram for every degree Celsius of temperature increase. Copper is slightly above that. It's also a good conductor because it has a low specific heat of 39 joules per kilogram per degree Celsius. If it transfers energy well, heat well, that means when I have that hot water going through my hot water radiators, it's going to allow that energy to transfer very quickly to the air because the energy is not being held by the copper. Okay, so aluminum is slightly higher, a little bit higher for us. Now, if we go up to, let's take a look at air. Air actually stores quite a bit of energy. This is one of the reasons why oftentimes when we touch a metal, it feels cool. Metal holds very little energy. So when we touch that metal, that energy, the energy it has, we feel the coolness because the heat from our hand gets transferred to that metal. Okay, so it gets transferred very quickly because metal, it takes very little to heat up that metal. Versus in air, it takes more energy. Air stores more energy, so it takes more energy to heat it, which means it's going to take longer for our body to cool down. Let's look at another one. Steam. Steam isn't quite as good. This would be water vapor. Water vapor. It's a little bit better than air. Water vapor. But the highest one of them all, the one on the list here that we have, the highest energy store is in Water. I don't have, other than on the last side, I had wax, which would be a hydrocarbon, which would maybe be the closest relation, which might be the closest that we'd have to thinking about oil, the amount of energy held by oil and whatnot. But water, I think, is the highest on our list. Water stores a lot of energy. So when it takes time for my boiler to heat up. But once my boiler heats up, because water stores so much energy, as water circulates through my pipes in the house, it's going to more slowly dissipate that heat, which will give us more even heating. So one of those little things of water, because it stores so much energy, there's a lot of energy it's able to release. The other thing is if our boiler turns off, we still want to have insulating jackets on it, but if it turns off, it's going to maintain that heat for a little bit of time. Ethyl alcohol is sometimes used in coolants. We'll often mix it with water. It has a pretty good specific heat, 2400, so it's right here at the top, but not quite as high. So it doesn't hold quite as much energy, but it's an energy sink, and because it holds so much energy, it's able to draw heat out of another object. So just a simple at-home thing that I often do, if I take sometimes I forget to take something out of the freezer for supper. So maybe it's hamburger and I wanted to thaw more quickly because I didn't take it out in the morning. I waited and I took it out maybe lunchtime. What I'll often do is I'll put it in water, and it thaws much faster if I put it in a bowl of water than if I just leave it out open to the air. And the reason for that is air holds much less energy than the water does. So the water is able to extract more energy from that meat, meaning it will thaw faster. So that's just some little ways we can use that table. I know you're not going to use them in that way for calculations here, but it's just kind of interesting to think about how some of those relate to things that we do every day without necessarily understanding why. The reason I will thaw my chicken out in a bowl of water is not because it's what my mother always did, because the science actually says it works. Sometimes those are good little tricks to know and little things that you can use to help you out. All right, so we're going to do a couple calculations with sensible heat. The calculation is really easy, and this is an equation. Let's get the right pen here. An equation that's really easy to use. Let me see. So the equation for sensible heat, if you remember it from the previous slide, I know I talked for a little while, so if you need to pause and go back, do that. But the equation for sensible heat is the change in heat is equal to mc delta T. So mass, the specific heat, and that comes from the chart. And then this is temp change. Now this has to happen within a single phase. So looking at this question, how much heat does it take to heat 6 kilograms of copper from 200 up to 240? So for this question, I know it's a sensible heat question. I mean, it says it, but I want to know how much heat. So the change in heat is what I'm looking for. I have a mass equal to 6 kgs. I have a temperature change, 240 minus 20 gives me 220. And the last thing I need to figure out is I need to find C. So let's look at our chart again. So we were dealing with copper, and it didn't tell us which units to use, but it did tell us we had kilograms. So let's use this one, okay? So joules per kilogram degrees Celsius, 390. So we'll go plug that back in our formula. 390 joules per kilogram degrees Celsius. Note, I've got kilograms here kgs and kgs, Celsius and Celsius. My units are all matching, which means the unit I'm going to get for energy is going to end up being joules. So we're going to put that into our formula. So heat, well, the delta H is equal to 6 kgs times C, which is 390, times our temperature change of 220. Multiply those three together and we have our answer. And you would get 51480 joules. Now you can probably see why they usually write kilojoules. It's a big number. So oftentimes what we'll see is we'll see this written as 514.8 kilojoules. We won't follow sig figs on this question or worry too much about our rounding, simply because I haven't been very precise in how I wrote the numbers in this question. So that's something I'll have to update later. So the amount of heat is 514.8 kilojoules. Okay, so we'll find, and I'll just make a note here that we found it in kilojoules. That's not something you would have known other than it's what I decided as we were working through the question. Most of the time your question will tell you. So if I have a chance, I'll do another video with a couple of the practice questions that give you a little bit of review. It'll probably be the weekend before I get an opportunity to do those ones. Let's take another one. This one, oh, I like this one. This one actually comes directly from the practice sheet. So if it looks familiar, it should be. It should be. So what is the specific heat of silicone if it takes 192 joules to raise the temperature of 45 grams of silicone by 6 degrees Celsius? So in this question, let's list the information we have. We know what's in, we're looking for heat. There's a temperature change, so it's sensible heat, and heat is equal to MC change in temperature. So I have a mass of 45 grams. I have a C. Well, I don't have C because it says what is the specific heat, so that's my C. So I'm looking for it. I have, excuse me. Oh, I have my heat. Heat equals 192. And I've got my delta T because it says the temperature changed by 6. So we'll put that into our formula, 190. It's getting too late to be doing this. I'm starting to blunder my words. Okay, our heat is 192 joules, is equal to a mass of 45 grams times C times 6 degrees Celsius. Now we're going to rearrange this. We want C alone, so we're going to divide by 45 grams and 6 degrees Celsius. We're going to do the same thing over here. Now you'll notice this is giving me my units already. I'm going to have joules per gram degrees Celsius. So when we calculate it, C equals, we know we're going to have joules, grams degrees Celsius. If you weren't sure, look at what units you have and then check the table and see what units are you allowed to have. And that's one way to kind of compare if you think you have the right unit. But I'm just using it simple algebra in order to figure it out. So the joules doesn't cancel on this side, grams doesn't cancel on this side, and Celsius doesn't. Here, these ones all cancel. So 192 divided by 45 times 6 gives me a specific heat of 0.70. 3 digits on our questions. 0.704 is our specific heat. So again, just really simple rearranging. That's what you would do if you're looking for something else in the question. I could also give you how much heat there was. You could look up C. You can know your temperature change. I can say, well, what mass of material did you heat? For example, how much water did you heat? If you use 3,000 kilojoules of energy and you had a temperature increase of 20 degrees, that would be a really nice style of question, which gets you thinking about how can you use the pieces to do a little bit more than just calculate heat. So it's just the same kind of question where you're rearranging. All right, so we've got one last type of heat to look at, and then we'll look at a couple of combination questions. I think I might hold the combination question until next time, but we'll see how it goes getting through this one. So latent heat. Latent heat is heat energy that's needed to change the state of a material. It doesn't cause a temperature change to occur, and it only depends on the mass of the object. So there's no temperature change, so temperature is not included in the formula. More mass you have, the more energy it takes. So if I wanted to turn 3 grams of water into steam, in order to know how much energy it would take, I just need to know how much energy is required per gram to change it into steam, because there's no temperature change that's occurring at that phase. So you're going to see there's 2 terms that we use. There's the heat of fusion. That's when we're going from a solid to a liquid, or vice versa. Now, one thing to think of, if you're making ice, ice takes energy, so you'd have negative energy. Okay, it's taking energy away. If you are heating something up, if you're making ice, it gives off energy, so you usually have a negative. If it's requiring energy, often it'll be positive. We're not going to get a huge amount into that. I find I like to use a picture graph in order to think of it, and that works quite nicely for us. And then for vaporization, you have to think, well, does it take it? Which one takes energy and which one gives off energy? So if I'm going from a liquid to a gas, it's always going to require energy. So I'm going to add in more energy. If I'm going from a gas to a liquid, it's going to give me back energy. So that's when things kind of feel cooler. So things going from a gas to a liquid. So for example, steam condensing on your hand feels cool, because when it condenses on your hand, it's taking energy. I think of how to say this the right way. I'm going to have to come back to that one. Every once in a while, I get myself tongue-tied. I kind of know where I was going, but we'll keep going. It'll come back to me. All right. So our 2 formulas. Formula for latent heat is just going to be mass times this L. This is the specific heat of fusion. This is from the table, and this is from the table. And I'll show you where those are in your table. Again, the table is posted separately on SAM. If you find it easier, print a table out and work alongside of it, but work along with it beside you. That would be especially useful for a test, because it's going to have all the formulas that you need to use. All right. So on the table, this table, it gives us the melting points of some objects, because the heat of fusion happens melting and fusion go together. Okay, so if your temperature changed, let's say we have water, okay, water, and we're going from -4 to +4. It's going from ice to water. I'm going to have a couple different heat curves if I want to find out how much energy that requires. So that's where I need to know my melting point. So see, if your temperature change happens if the temperature change occurs across that melting point, that tells you we're going to have to add in latent heat. Or if you have ice at 0 degrees and you want to know how much energy it is and there's not temperature in the question, that's a good time to double check and see, does that happen to be the melting point? Boiling point goes with, draw this way, the heat of vaporization. Okay, so fusion is the energy in order to go, this is the solid liquid, and this one is going to be liquid gas interface. Okay. Again, we're going to use our units the same way. You'll see there's kilocalories and kilograms, calories and grams, joules and kilograms. BTUs don't happen to be in this particular chart, so we're not going to worry about them for these questions. Again, we'll show you how to find the information from that in a minute. You'll notice a lot of these values, we have scientific notation. These are very large numbers, meaning it takes a lot of energy, so we'll give you a video that refreshes how to put that scientific notation in the calculator. All right, so if I'm heating up, let's say this, we're going to say this is water, because I know where all the temperature curves are. Let's say this is water, and we're heating it up. When water is a solid, we have ice. So I have ice. I put in energy, and I get to a point at which that ice melts. When that ice melts, I'm at 0 degrees. I continue to put in energy, and at this point, all of the ice turns into liquid. So now, in this phase, I have water. Once all the ice is turned to water, the temperature starts to increase again, and I get to the next point. Now this point, the next flat spot, is where we have 100 degrees Celsius. This is my, I'll call it boiling point. Okay, this is my boiling point. Down here, this is our melting point. Now I have to use BP and MP for boiling point and melting point, because those are common abbreviations that get used, and it's abbreviations that I always used when I was in university. So you'll see me abbreviate with that, especially since my writing on the screen isn't quite as perfect as it could be. And then you continue, if you continue to put in energy, you can continue to heat that gas up until the molecules get too far apart to really have much to notice an effect, I guess. But we're not going to have to worry about getting the point where we're basically blowing things apart. Okay, so this is our curve. So we add energy. So let's say we have, maybe this is minus 25 degrees. Okay, we add energy, it starts to melt, and at the melting point, it holds at 0 degrees. It stays, there'll be water and ice in equilibrium here. So it changes state. After it completely changes state, then it's able to increase in temperature again. It gets to another point, and that's where the next phase change happens. And at this point, you'll have water and steam in combination until all of that water is turned into gas. So that just gives you an example of what one of those curves looks like. And I find it sometimes helpful to sketch that in order to figure out how much energy is given or how much energy is taken, because I can kind of see, oh, this curve is different than this curve, so I'm going to require two different calculations. So let's do a quick calculation with latent heat. This question says, how much energy is needed to turn 2 kilograms of water at 100 degrees Celsius into steam at 100 degrees Celsius? So this is latent heat because we have no temperature change. So no temperature change tells me it's latent heat. And the formula for heat, there's no temperature change, it's just equal to M times L. Now let's see, is this going to be L of fusion or L of vaporization? So water is going to steam. So steam is vapor. So that's how I remember that it's vaporization. Okay, so it's going to be M times L. The mass of water was 2 kgs. And this time let's find it in calories. Actually, we'll use kilocalories, okay? Let's find out how much energy we need in kilocalories. So we have mass equals 2 kg and I need to know what is the L of vaporization. So let's see if it's on our chart. So looking at our chart, we had water and it's going to steam. So here's liquid water. And if I go across the chart, I don't have anything here for vaporization. What do you do? Well, what's the other name for water? Oh, sorry, I jumped a line. I jumped a line. We do have something here. Sometimes, my bad. My bad. All right, I jumped a line. We go across, let's see if I can follow a nice even line. Bigger gap here. Okay, so here is our water, and there's our vaporization. Now, something to keep in mind is sometimes you'll have water that's freezing, and water that's freezing, you would look under ice. So ice is solid water. Just one of those things to keep in mind when you're doing the problem, okay? Because that sometimes comes up. People go, I can't find it on there, and look and see if there's another term. So we're looking for the L for water to vaporize it. So vaporization. So we're looking on this column, and we want in calories. So we're going to use this one. So if I go down, I need 540 kilocalories per kilogram. So let's go back and put that in. So it's 540 kilocalories per kilogram. And if we plug that into our formula, we will get 2 times 540 gives me 1,080 kilocalories of energy. Okay. All right. Now a quick question to compare types of heat. I like this question. I've never really thought about it before until I found this in a book. So it's not an original, but it's a question that I really, really, really like. So, okay, we think boiling water, don't put your hands in boiling water because it hurts. Fair enough. But having 100 degrees Celsius, so boiling water is 100 degrees Celsius, and we say that that's dangerous, but 100 degrees Celsius on your skin, I've done that before. I've done it before, and it hasn't done anything to me. For example, I mean, have you ever put your hand in an oven that's at 425? It's a common temperature to do a pizza. Now, you taking the pizza out, I usually have my oven mitt on, but when I'm putting the pizza in at 425, I put my hand in the oven and I don't get blisters. So why, when the oven is at 218 degrees, does it not blister my hand, but yet a splash of boiling water and you can have third-degree burns? What's the difference? Well, the difference is how much energy those materials have. Okay, so for example, and we're going to simplify this because it's a little bit more complicated than the question here, but it works quite well for purposes. So let's figure out, if the air in the oven has a mass of 100 grams, and when you put your hand in, that air decreases 5 degrees Celsius. So you absorb that much energy by your hand. How much energy was transferred to your hand? Because it's that energy that's going to create the blisters for us. Well, let's figure it out. That's the heat that causes the damage. So, well, this question, I have a temperature change. I have a mass. As soon as I see mass and temperature change, I know I'm going back to sensible heat. So this is a sensible heat. And I'm going to figure this out. We're going to figure out joules for both cases, okay? So we'll use joules. So sensible heat, we've got, because we've got a temperature change, So let's figure out. So the heat that my hand would have absorbed is equal to the mass of the air times, because whatever heat was lost by the air must have been absorbed by my hand, assuming it didn't go into the rest of the kitchen. So it's MC, change in temperature. So let's plug our numbers in. So for mass, we have 100 grams. Which is equal to 0.1 kilograms. I'm going to just adjust some units here. The reason I switched that to kilograms, in case you didn't notice, is I said, well, let's do this in joules. And if I choose joules, I need to have kilograms and Celsius. So I'm going to have to switch my mass. So 100 grams is 0.1 kgs. Actually, 100 grams of air is quite a bit. C is equal to my 1,000 times 5. Okay, so 0.1 times 1,000 times 5. Did you get a calculation? Hopefully you got 500 joules as well. Okay, so 500 joules of energy is absorbed by my hand. So that's 100 grams of air. I think when I did numbers for this question, I'm pretty sure I actually kind of did rough calculations based on the cubic feet in an oven and the density of air. I couldn't guarantee that, but 100 grams of air, that would be, it's a pretty reasonable number for the amount of air that was changing temperature. Now, let's say, okay, so let's take the same scenario and let's say we have steam, because steam is what burns in the kettle. So this time, instead of putting my hand in a dry oven, I'm passing my hand over a kettle. I know you know that if you have a steamy oven, it hurts worse. I actually took a pan out of the oven the other day and I got myself a good little scorch just from the steam off it. So let's look, why does steam at 100 degrees Celsius burn you? So we said air, so 100 grams of air with a 5-degree temp change equals 500 joules, okay? So this is just for comparison. Now let's calculate, okay, let's say we've got a similar scenario. This time, I just have all that happens is the steam condenses on my hand. We're going to ignore what's happened to the energy as it cools down. That's going to add even extra energy to it. But I want to know how much heat is released by the steam because that's going to be absorbed by my hand. Now you can probably guess. If I'm getting burnt with steam, there must be more energy. So let's figure it out. Now this question doesn't have a temperature change. So because we have no temperature change, we have latent heat. Okay, so our formula for that, the amount of heat is going to be M times L, and it's going to be L of vaporization, which we had before. So the mass, well, let's double check our units first. Okay, so let's check our units. So water, vaporization of water, here we are here. So we need this number, which is in joules per kilogram. 2.26 times 10 to the 6. Now I'm going to erase a little bit of that just so that if you are going over this after, you can actually read the numbers, would be really useful. Okay, so we're going to find it in joules because we want to compare apples to apples. So 2.26 times 10 to the 6. Now, when you see that times 10 to the 6, you know you're going to get a big number. That should be our first clue that we're going to have a lot more energy. What did I say that was? 2.26. And that's joules per kilogram. So putting that into our formula, I need to have 100 grams is equal to the mass, which is equal to 0.1 kgs. So 0.1 kilograms times 2.26 times 10 to the 6 joules per kilogram. Multiplying those two together, you get 226,000 joules of energy if there was 100 grams of steam. Even if you only had 1 gram of steam, 1 gram of steam would still give us 2,260 joules. Either way, it's a massive amount of energy. And because water holds so much more, even steam holds so much more energy than air, that's one of the reasons why steam burns us and air doesn't. It's also proof to us that energy is required when making steam, because energy is released into our hand to a point that it causes burns when we pass our hand over steam. So those are just some practical examples that help to prove to us why energy is required with latent heat. It's also one of the reasons why there's big signs on your boilers to let it cool down before you open it. I even have an iron that has a water reservoir on it. I don't always follow the rules, but I'm supposed to let it cool down for 2 hours to come to temperature because of the steam that it holds. There are a few tricks if you're in a hurry and you need to speed things up, but in general, make sure you follow the rules, because water, especially if you were dealing with steam, and if you guys are working on servicing a boiler, watch those temperatures, because you could definitely get some really, really nasty burns just due to the energy that is stored by that steam or by the water. All right, we're going to do one combined heat calculation, and I'm just going to take a peek, and that'll be the end of our lesson here, and we'll get the next lesson posted up for you shortly. How many calories of heat are needed to melt 450 grams of ice at 0 degrees Celsius and to raise the temperature of the ice to 80 degrees Celsius? So this is a two-step question. How do you know it's 2 steps? Well, I like to go back to this picture, and it helps me figure it out. So we have ice at 0 degrees. So I have ice here. On this side, I have ice. On this side, I have water. So I'm at this point. So I have ice at 0, and I'm going to bring the temperature of it up to 80 degrees. So first of all, the ice turns to water. What's the heat? Okay, let me just adjust here a little bit. Okay, so ice to water, we want to know how much heat does that require. Then I need to find out water, because the water is going to be at 0 degrees initially. The water at 0 degrees to 80 degrees, how much heat? So this one is latent, and this is sensible. So you've got 2 different states happening. Now you may need some extra practice questions on this, and I'll do a couple videos with some extra questions if you need them. So first of all, let's do the ice to water. So that's latent heat, so it's going to be M times L. Okay, sometimes you'll see in books they'll use Q instead of H. I like H. H and heat start with H, so it makes it easier. So the mass of our water is 450 grams. I need to know what is the L for water. So if we go back to, here's water, and actually water, I don't have my heat. This is fusion I'm looking for. I'm not looking for vaporization this time, so let's just erase vaporization so we don't get mixed up. So we want to find where is ice to water, okay? So ice, here's ice, and here's water. So we're going from ice to water. So we need to know the heat of fusion. Fusion is like the heat required to fuse the molecules together to make a solid. So we want calories. We're going to use this number, 80 calories per gram. Okay? So we'll plug that in our formula. 450 times 80 gives us 36,000 calories. All right, so that's part one. Part two is how much heat is required to change the temperature. So we want to know the sensible heat. So heat is equal to mc delta T, which the mass of water stayed the same, or the mass of the ice, all of it was converted. So we'll assume our mass is the same. So 450 grams times, now let's look up our C. So for water, we want the specific heat this time. And I want it for water. This time I don't have ice. So this time I want to use water. And this, because that's all been converted to water. So the specific heat of water is 1 calorie per gram. So 450 times 1 calorie per gram. And then I have gone from 0 to 80 degrees. So times 80 degrees Celsius. Sorry, that's really, really hard to see. I suppose I should make it legible for you. It won't take much to do. I can squeeze her all in there. All right. So heat is equal to 450 times grams times 1 calorie per gram degrees Celsius times 80 degrees Celsius. Get everything squeezed in there, and that gives us another 36,000 calories. The total is when we just add the two together. So it requires energy to melt the ice, it requires energy to heat it up. So this is to heat water. So our total, well, we'll just get 72,000 calories or 72 kilocalories, whichever one you happen to want to have. So I'll give you some more examples of that one later. That's the one that usually people have a little bit of more complication with. You can expect to see one of those. You will see one in your practice quiz. All right, so you should be able to do that practice quiz. I'm going to guess you could probably even do the practice quiz for this section before you see the fourth video. The fourth video will be a nice short summary, but I will throw another one of these calculations in for you.